Why does a black hole glow? Wait, you've been told black holes are black. Nothing escapes, not light, not matter, nothing. That's not a little wrong, fundamentally wrong. Here's a fact. A black hole the size of a pinhead would outshine 1 billion suns, glowing, screaming radiation into space. Right now, you've seen that orange ring photograph. You thought it was gas falling in, stuff outside the hole. No, the black hole itself radiates from its edge, from the boundary where space-time ends. Here's where your reality cracks. This glow isn't matter escaping. The universe creates particles from nothing, rips them from empty space because gravity tears the vacuum apart. This changes what emptiness means, what darkness means, what nothing actually is. I spent my life asking nature questions she didn't want to answer. This one she whispered so quietly it took humanity 50 years to hear. And once you understand this, truly understand, you'll never look at darkness the same way again. Let me show you. Put your hand near a hot stove. Don't touch it. You feel that? Heat reaching across empty air, touching your skin from a distance. Now here's the question nobody asks. How does that heat reach you? Nothing is traveling, no air blowing, no contact, yet energy crosses the gap. That's radiation. Everything with temperature glows. Everything. The stove glows red when it's hot enough to see, but even when it looks dark, it's still glowing. Infrared, invisible to your eyes, visible to the universe. Your body glows right now. 60 watts of infrared radiation pouring off your skin. You're a light bulb, a dim one, but a light bulb. Here's the part nobody tells you about emptiness. Space itself has a temperature. Empty space. The void between galaxies. The nothing between atoms. Not zero, close to zero, but not zero. And if it has temperature, it must glow. This is where your intuition lies to you. You think emptiness means nothing is there. No particles, no energy, no activity. Wrong. Emptiness is buzzing, fizzing, particles popping in and out of existence so fast you can't catch them. Borrowing energy from the universe for a fraction of a second, then vanishing. This isn't philosophy. This isn't metaphor. This is measured physics. And here's the connection you need to hold in your mind. If empty space buzzes with activity, what happens when you put the most extreme object in the universe right next to that buzzing? What happens when a black hole meets the quantum foam? Something breaks, something tears, and light comes out of darkness. Think about what just happened. I told you a hot stove glows. I told you empty space has temperature. I told you the vacuum is alive with ghost particles. None of that sounds connected to black holes, but it's everything. Picture the edge of a black hole, not inside, not outside, the exact edge, the event horizon. This is where space-time bends so sharply that light itself curves back, where time slows until it nearly stops, where the rules you know stop working. Now remember those ghost particles I mentioned, the ones popping in and out of empty space. Here's what happens at the edge. Two particles appear from nothing, a particle and its antiparticle, born together. They're supposed to meet, annihilate, vanish back into the void. That's the deal. Borrow energy, pay it back instantly. But at the event horizon, something goes wrong. One particle falls in, the other escapes. Wait, the pair gets ripped apart, separated by gravity so extreme that space itself can't heal fast enough. One partner crosses the edge, gone forever. The other shoots outward into the universe. That's Hawking radiation, not stuff escaping from inside. Nothing escapes from inside. The prison is perfect, but the prison wall, the wall is leaking. Let me say that slower. The black hole isn't releasing particles it swallowed. It's causing new particles to be born at its boundary. And one half of every pair steals energy from the hole itself. Steals. Every photon that escapes makes the black hole lighter. Every particle that flies away shrinks the hole by a tiny amount. This is where it gets stranger. The black hole is evaporating, not dying from starvation, not collapsing, evaporating like water from a puddle on hot concrete, molecule by molecule, photon by photon. The most permanent objects in the universe, the things we thought would outlast stars, outlast galaxies, outlast time itself, are slowly dissolving into light. Impossible until you see the trick. The trick is this: the energy for those escaping particles doesn't come from nowhere. It comes from the black hole's mass. Mass is energy. Einstein told us that. E equals mc squared. So when a particle escapes, the hole pays. And if it keeps paying, eventually it goes bankrupt, gone. A black hole can die. Now here's the question that should be forming in your mind. How fast? How long does this take for a black hole the size of our sun, longer than the current age of the universe, multiplied by the age of the universe, multiplied again, but for a tiny black hole the size of a mountain, seconds. And in those seconds, it doesn't whisper radiation. It screams. Cambridge, England. A man in a wheelchair sits alone in his office, 3 in the morning. Everyone else has gone home. Stephen Hawking. His body is failing. Motor neuron disease has taken his legs, his arms. Soon it will take his voice, but not his mind. Never his mind. And tonight, his mind is on fire. He's been thinking about black holes for months. Everyone says they're perfect prisons. Nothing escapes. Entropy goes in and disappears. Information dies. But something is bothering him. A whisper in the equations. See, there's a rule in physics, a deep rule, thermodynamics. If something has entropy, it must have temperature. If it has temperature, it must radiate. Black holes have entropy, enormous entropy. Jacob Bekenstein proved that the year before. So black holes must have temperature. So black holes must glow. Hawking runs the numbers. This is what he saw at 3 a.m. The mathematics spit out an answer nobody expected. Not hot, cold, incredibly cold. A black hole, the mass of our sun, would have a temperature barely above absolute zero, but not zero. And not zero means radiation. Hawking checks his work, checks again. The answer doesn't change. Black holes radiate. He thinks he's made a mistake. For weeks, he searches for the error. There is no error. Here's the part that broke physics. If black holes radiate, they lose energy. If they lose energy, they lose mass. If they lose mass, they shrink. If they shrink, they get hotter. If they get hotter, they radiate faster, 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 until the end. The last moment of a black hole's life would be an explosion, a flash of gamma rays and particles, everything it ever swallowed, released as pure energy. Black holes are not eternal. Hawking publishes. The physics community goes into shock because this wasn't just about black holes. This was about everything. Quantum mechanics and gravity, the two pillars of physics, had never talked to each other. Einstein's relativity over here, quantum theory over there. Nobody knew how to connect them. Hawking connected them at the edge of a black hole, at the event horizon, where gravity is strongest and quantum effects are most violent. That connection told us something profound, not philosophy, measured implications. The universe has rules that cannot be broken, not even by black holes, not even by the most extreme objects in existence. Entropy must be paid. Temperature must radiate. Nothing gets to hide forever, not even darkness. Let me prove this to you. Not with equipment, not with telescopes, with logic. Close your eyes. Imagine a box, perfect vacuum inside. Nothing, not one atom, not one photon. Pure emptiness. Now here's the question. What's inside? You want to say nothing. Wrong. Heisenberg won't let you. The uncertainty principle says you cannot know a particle's position and momentum perfectly at the same time. The more precisely you know one, the less precisely you know the other. But here's what that really means. If you say a box is perfectly empty, you're claiming perfect knowledge. You know exactly how many particles are there. 0. You know exactly where they are. Nowhere. That's too much certainty. Nature doesn't allow it. So what does nature do instead? She fills the emptiness with possibility. Particles flicker into existence. Antiparticles beside them. They live for a billionth of a second. Then they annihilate. Gone, but they were there. They were. Energy borrowed from the universe, paid back before anyone notices, like sneaking money from the register and returning it before the count. This isn't theory, this is measured. These ghost particles, virtual particles, they have real effects. They shift energy levels in atoms. They change how electrons behave. We've measured those changes to 12 decimal places. The vacuum is not empty. Hold that thought. It shatters now. Because if the vacuum everywhere is fizzing with these temporary particles, then the vacuum at the edge of a black hole is fizzing too. And at the edge, something stops them from annihilating. Something rips them apart. You want proof you can touch? Here it is. Dutch physicist Hendrik Casimir makes a prediction. Strange prediction. Sounds like madness. Take two metal plates, perfectly flat, perfectly clean, put them in a vacuum. Bring them very close together, almost touching. They will push toward each other. No magnets, no charge, no force you've ever heard of. Nothing pushes them, literally nothing. Here's the trick. Remember those ghost particles fizzing in empty space? They have wavelengths, like light, like sound, different sizes. Outside the plates, all wavelengths can exist. Big ones, small ones, every size. Between the plates, only small wavelengths fit. The gap is too narrow for big ones. So fewer ghost particles between. More ghost particles outside. The outside pushes harder. The plates move. Not philosophy. Measured. Steve Lamoureux measures the Casimir force directly. The plates move exactly as Casimir predicted. Exactly. We built machines using this effect. Nanotechnology. Microelectronics. Engineers have to account for it, or their devices fail. The vacuum has pressure. Emptiness has weight. Nothing has force. Let me say that again. We measure the force of nothing. We engineer around the pressure of emptiness. We build technology that would break if the vacuum weren't fizzing with ghost particles. This is not theory anymore. This is your phone, your computer, your world. Now scale it up. If two metal plates experience this force, what about space-time itself being bent? What about the most extreme curvature in the universe? What about the edge of a black hole? The effect doesn't just happen there. It explodes. Now let's go extreme. Imagine a black hole, not the giants in galaxy centers, not the monsters eating stars, small, the mass of a mountain, compressed into something smaller than an atom. Hold out your hand. It would fit in your palm. You're not ready. Here it is. That tiny black hole would be glowing at 100 billion degrees, hotter than the center of any star, hotter than the first second after the Big Bang. Your hand would vaporize, then you would vaporize, then the city would vaporize, not from falling in, from the light coming out. Here's the rule. Hawking discovered. Small black holes are hot. Big black holes are cold, backwards from everything you'd expect. A black hole the mass of our sun. Temperature of 0.06 degrees above absolute zero. Colder than empty space itself. So cold it actually absorbs more radiation than it emits. But shrink it, the temperature rises. The mass of Earth, a few degrees. The mass of a mountain, billions of degrees. The mass of a car, explosion, immediate, catastrophic. A burst of energy equal to 1 billion nuclear bombs. And here's what that means. If tiny black holes existed from the Big Bang, primordial black holes, they'd be dying right now, exploding, flashing gamma rays across the cosmos. We look for those flashes. So far, nothing. But the absence tells us something too. It tells us about the early universe. What happened, what didn't. Black hole radiation isn't just theory, it's a telescope. Pointed at the beginning of time. So far we've learned black holes glow. They radiate, they evaporate. But that's not the deep truth. The deep truth is stranger. It's about information. When something falls into a black hole, a book, a star, a person, what happens to the information? The arrangement of atoms, the pattern that made it unique. For decades, physicists said, gone, destroyed, erased from the universe. Hawking said this himself. Information dies in black holes. But here's the problem. Quantum mechanics has a rule, unbreakable. Information cannot be destroyed, ever. It can be scrambled, hidden, spread thin, but never deleted. Two pillars of physics, contradicting each other. This became the information paradox, and it started a war. Hawking on one side, every quantum physicist on the other. 30 years of arguments, papers, conferences, bets, real bets, money on the table. Here's where it gets stranger. The radiation coming from a black hole, Hawking radiation, it seems random, thermal, meaningless, like static on a dead TV channel. But is it? Some physicists now believe the radiation is encoded, scrambled beyond recognition, but not random. The information is coming out slowly, painfully, hidden in correlations we can barely imagine. The black hole isn't destroying information, it's encrypting it. Think about what this means. Nothing truly disappears, not from the universe, not ever. Every pattern, every arrangement, every piece of what makes you, you. The universe keeps records, perfect records. Even black holes, the ultimate erasers, cannot delete the cosmic ledger. This is why black holes must die, not because physics is cruel, because physics is honest. If black holes lived forever, they would be vaults of stolen information, locked away eternally. That breaks the rules. So the universe forces them to pay it back, photon by photon, lifetime after lifetime, until nothing remains but the information they tried to swallow, returned. The universe refuses permanent secrets. Not even darkness gets to keep what it takes. Let me leave you with this. You started this video thinking black holes were black, dark, silent, the end of everything. Now you know different. Black holes glow because emptiness is not empty, because gravity can tear the vacuum, because temperature cannot be hidden, because information cannot be destroyed, because the universe has rules even monsters must follow. Beautiful. I spent my life chasing nature's secrets, asking questions that made people uncomfortable. This question, why does darkness shine? It's one of the deepest we've ever asked. And the answer? The answer is hope. Nothing lasts forever. Not stars, not galaxies, not black holes, not even the darkness that swallows light. Everything returns, everything radiates, everything gives back what it took. The universe is honest, brutally honest, patiently honest, even if it takes longer than the age of everything. The debt gets paid. So next time you look up at the night sky, next time you see darkness between the stars, remember that darkness is glowing, faintly, slowly, but glowing. And one day, inconceivably far from now, even black holes will become light. Nothing hides forever, not even nothing.